Hello, welcome to my physics report for 2211, going over constant velocity motion. The goal of this lab is to apply Newton's second law to real-world observations of theoretical constant velocity motion. Through this, we'll be able to test the applicability and accuracy of his law, as well as the viability of our own observations. We'll do this through the comparison of position versus time graphs of our own observations and a computational model that is made to mimic an idealized version of these observations. Because this lab focuses entirely on Newton's second law, it's very important to understand the general concepts as well as some formulas that can better explain this law. His law states that the forces acting upon a system change the system's momentum over time. His law dictates that if no net forces act upon a system, then the momentum will not change and velocity and direction will remain constant. The two formulas that are useful for this are the momentum update formula and the velocity update formula. They look very similar and can be derived from each other because momentum is equal to velocity over mass. One of the most important things to see in this is that if the F variable, which is the net force, is equal to 0, then both of these terms cancel out completely, and both the momentum and the velocity will equal their initial values. The forces in this definition can be better thought of as the net forces, because if there are many forces that all sum to 0 and cancel out, the impact on the system will be the same as if no force was applied at that moment. The system in this definition is defined by the observer, and it's generally the object or group of objects that is being acted upon or not acted upon by the surroundings and being gauged for its change in position or velocity over time. The general procedure for this lab was to observe constant velocity in an object and then record and track a calibrated video of it. In my lab, I got a ball and rolled it on a flat ground and used the tracker calibrated video tool to observe data points and then create a graph of this. You then create a computational model to mimic what you've observed and then compare the results to see how the idealized version versus the observed version compare to better draw inputs into how this law actually applies in real life. So in this lab, the air resistance and friction are supposed to be treated as negligible. So once my hand lifted off the ball, I set that as the origin, and then there shouldn't really be any forces acting upon the ball in an idealized system. So the initial velocity of the ball I found to be 1.24 meters per second, which I calculated from the position at the origin compared to the position at 0.102 seconds. This was a small enough gap that I could get a semi-accurate gauge of initial velocity, but not too small to where the error of me clicking on what I thought was the middle of the ball would remain constant and mess that up. This code is initialized with the ball's original mass, starting position vector, and starting velocity vector, which I got from my observations. And then there's a while loop that updates the ball's velocity and the ball's position as the time advances. So in this, the ball's velocity doesn't change because there should theoretically be no forces acting upon it, and then the ball's position updates by the velocity vector, which isn't changing. So here on the left, I have the model, which shows a ball going to the right, much like the rolled ball. This graph demonstrates the differences between the computational and observed model. The computational model demonstrates consistent velocity as no forces are applied in the glowscript code. Unlike this, the observed model, while initially overlaid, eventually lags behind as the velocity is decreasing. This is because of friction and air resistance, as well as likely some bouncing of the ball, slowing down its x-directional value. This demonstrates how the computational model doesn't take into account real-world circumstances of forces acting upon it and how there were forces applied to the observed model, despite from an eye view, maybe it seems like pretty consistent motion. If the axes were flipped in this, then the X direction would be updated negatively and the velocity would also be negative. This wouldn't change the general implications of net forces acting upon velocity and momentum. It would kind of just change the way that the data is analyzed. So in this we said net force equals 0. This means all the forces sum out to equal 0 or there are no forces at all. So in the observed model, the friction and air resistance showed how there was forces applied, slowing down the velocity, unlike the computational model. Thanks for watching.